Morning, everybody. I'm standing in for Mary today. She's sick, so she'll continue from Thursday onwards. Just before we begin the session, I think quiz 1 will be open this Sunday. Yep. Oh, you're fortunate. You're given 2 weeks to... "45 minutes per attempt, and you have a maximum of 2 attempts. So do that as soon as possible. Okay, today's lecture, let's quickly revise what you will have done last week. We've introduced differentiation and limits and continuity, I believe. Yep. So today's coverage involves both chain rule and implicit differentiation. These are techniques of differentiation at the next level, because I think probably last week you did this. Power rule, product rule. When do we use product rule? When 2 functions are multiplied? Yep, then you use the product rule. And quotient rule. When do we use quotient rule? When 2 functions are divided. Okay, this is all about differentiation. It is part of calculus. Why study calculus, by the way? Where is calculus used? I'm assuming some of you take accounting economics. Yep. So in economics, there's a major use of differentiation in economics. We talk about marginal cost, maximizing profit, minimizing the cost, or minimizing expenditure. I think you will be using that in a 100 level or 200 level accounting and economics. For those of you who wish to pursue engineering, differentiation is used in stress analysis. Circuits, physics, for those of you who will pursue physics, its application of differentiation is you're shooting a projectile up in the air. What's the maximum height reached by the projectile? So these are applications of differentiation, so that you know. One of the main applications of differentiation, you came by bus this morning, a car. On the road you came across, what you call this, the lights on the crossings. You have the lights turn green, and then amber, and then red. All of those are applications of differentiation. So this is not something theoretical, it's applied. We have the widespread use of Prius cars, Prius vehicles. There's a whole lot of differentiation applied there. And for those of you who wish to pursue IT, that's big use of differentiation and integration. So this is applied, It's applied. So like I said, we will touch on chain rule and implicit, if time allows. If you did MAF11, composite function was covered in MAF11. Yep, where there is an inner function and an outer function. Here's an example. Y equals square root of x squared minus 4x. This is a composite function. What's the inner function here? x squared minus 4x and the outer function. So in other words, you can write it in this form, to the power of half. You cannot use product rule, you cannot use quotient rule here. But we identify this as the inner and to the power of half as the outer. And this is a case where we apply chain rule. So let's have a look at in this case, the inner function is gx, and the outer function is f of x, or f of gx. And the chain rule says, if you are to find f dash x, if you are to differentiate fx, then we will differentiate the outer function first. The inner function remains unchanged. Yep. And then multiply by the derivative of the inner function. Let me say that again. Differentiate the outer. Leave the inner as it is. And then multiply by the derivative of the inner. I think this is in your course book. Keeping the inner function the same. And then differentiate the inner and then multiply them. So let's have a look at some examples. Again, in this case, you cannot use the chain rule, you cannot use the product rule, you cannot use the quotient rule. Okay. Oh. Let's see. Y equals x cubed minus 2x, everything to the power of 5. What's my inner function here? X cubed minus 2x. Yes, outer function? To the power of 5. Now, the chain rule says you differentiate the outer first. So what's the derivative of x to the power of 5? 5x to the power 4. And then we will leave the inner as it is. All right, the derivative of the inner, or the inner function is x cubed minus 2x. The outer is x to the power 5. So the suggestion was we differentiate the outer. I would prefer to write this as something to the power of 5. I don't like to use the x there. So if you differentiate the outer to the power of 5, so it becomes 5 something to the power of 4. And this something is the inner function that remains unchanged. Five. The power now becomes 4, and the inner function remains the same. And then we will differentiate the inner. What's the derivative of the inner function here? Differentiating x cubed minus 2x gives us 3x squared minus 2 and multiply to this. And we expect you to rearrange from here onwards. Now, it's up to you. You can leave it as it is, or you can decide to move this to the front. What do we have here? There. So we've differentiated the outer. X to the 5, 5x to the 4, and we've left the inner as it is, multiplied by the derivative of the inner. All right? Let's have a look at another example. Y equals cubed root of 2x squared plus 5x. We can write cubed root as a power. What's the power representing cubed root? To the power of? Cubed root? To the power of 1/3, yes. What's the inner function here? 2x squared plus 5x. Outer function? To the power of 1/3. I give you 1 minute. See if you can differentiate this first. Y equals 2x, what was it? X squared or x cubed? X squared, okay. So the inner function is outer function give it a go. G dash x is easy. What's the expression for G dash? 4x plus 5, agree? And F dash, power of 1/3. What's the derivative? Will bring the power down, will reduce the power by 1. So bringing the 1/3 down, this will be 1/3 something. What's the new power, by the way? 1/3 minus 1. Negative 2/3, eh? So that means 1/3. What should I have in here? The gx, the inner function remains unchanged. So that means, and then we will fulfill, because we have y, we'll have dy over is equal to f dash gx times g dash x. So what's f dash gx? Multiplied by g dash. And again, like I said, we expect you to simplify. Of 2/3. And we've differentiated the inner. So dy over dx is 1/3 4x plus 5, 2x squared plus 5x, everything to the power negative 2/3. Another example. Negative 12 times 4th root of 6x squared minus 7x. If we rewrite it properly, what's the power representing 4th root? To the power of 1/4, yes? Now, inner function. What's the inner function here? 6x squared minus 7x. Outer, negative 12 to the power of 1/4. Right? So hx, let's, again, I'll give you 1 minute. So the inner function is so g dash, outer function, let's say, is negative 12. So what's f dash? Yep. Inner, by the way, g dash, what do we get? Differentiate this, we get 12x minus 7. I'm interested in f dash. What do we get? Differentiate, go on. So the negative 12 remains. And then I'll bring this power down. What's the new power? 1/4 minus 1 is negative something. Negative 3/4. And what goes in here? Gx, the inner function, eh? What is it? 6x squared minus 7x. There you go. And from here onwards, because you've got hx is equal to f dash gx times g dash x. What's f dash gx? Oh yeah, we can multiply this too. What does it give us? Negative 3. Multiplied by g dash. Where's g dash? And then you can rearrange. There. Multiply by, so remember how we got this negative 3? Where did we get the negative 3 from? We multiplied negative 12 with the original function since we differentiated the outer, and then multiply this by g dash. So what are the general steps? Identify the inner and outer. Differentiate the inner, differentiate the outer, leave the inner as it is. Then multiply by the derivative of the inner. This looks like a use of quotient rule because we are dividing. The suggestion is, if there's just a number on the numerator, if there's a number only on the numerator, do not use quotient rule. You might as well move this up to the numerator. You only use the quotient rule if the numerator and denominator are both functions. Okay? If only the numerator has a function, you don't need to use the quotient rule. And in this case, if the numerator is not a function, don't use the quotient rule. The suggestion is you move this up. So if you move that up, so we have an inner and outer function. What's the inner function here? 3x squared minus 4x, yes. Outer, negative 3 to the power negative 4, negative 5. Z. Negative 5 to the power of negative 3. So, let's cut down on our steps. So we'll differentiate by working on the power. We'll move the power down and reduce the power by 1. So what will we have? I'll multiply negative 5 and negative 3. What's the new power, by the way? Negative? Negative 4 here. Negative 3 minus 1. What goes in here? The inner function remains unchanged. And then we will differentiate the inner. What's the derivative of 3x squared minus 4x? 6x minus 4. And simplify. If you are, okay, let me say this. I'm just talking about me. If I am a crazy mathematician, then I don't like how this looks. I would prefer to write it formally as, if I write it properly, what is it? All of these divided by is to the power of 4. This looks better for me. But this is fine. Yeah? If you are scared of making mistakes, okay, leave it there. Again, same case. The numerator is just a number, so don't use quotient rule here. Move this up. Square root, what's the power representing square root? To the power half, and then we move it up to the power negative half. Identify your inner, identify the outer. So let's differentiate the outer. Move the negative half to the front, multiply it to this, and reduce the power by 1. What will the new power be? Negative half minus 1. Please change the power to an improper fraction. Don't write it as a mixed number. So I think it's negative 3 over 2. Yep. And this remains untouched, the inner function. And then I'll differentiate the inner function. And again, like I said, rearrange it. Write it properly. Again, I don't like the look of this. If you like maths, see if you can rewrite this properly. So, difficulty level increases here. Differentiate y equals 8x cubed times 3x to the 4 minus 2, everything to the power 5. This looks like two functions multiplied together. So if we have two functions multiplied together, what technique of differentiation do we use? That's one function. That's the other. So if that's the case, then I will have to use the product rule. Product rule says Okay, let me just differentiate f dash, I get 8x cubed. G dash. G dash looks like a composite function. So to get G dash, I'll have to use the chain rule here. So if I use the chain rule, I'll move the 5 to the front, reduce the power by 1. Inner function remains the same, and then differentiate the inner function. So if that's the case, there. I've changed the power, reduced the power by 1, I've multiplied by the original power, and the inner function remains the same, then I've differentiated the inner. Now, I expect you to simplify this further. Well, in actual fact, you can multiply the 5 and the 12x cubed, right? What does that give you? 5 times 12, 60. X cubed. Now, then we will apply the product rule. And what does the product rule say? F times G dash plus G times F dash. So we'll just slot in those expressions. F times G dash plus G times F dash. Again, we expect you to simplify this further. If you leave it as it is, we'll deduct marks because this is not the simplest we can have. I can multiply these two, and I can move the 24x squared to the front. That looks better. So that means the chain rule cannot be questioned in isolation. It will be attached to some other techniques of differentiation. Here in this case, we use the chain rule embedded in product rule. So that means there will be questions where we combine chain rule and quotient rule. And there are also cases where you'll have to use chain rule more than once. That means we have an outer function and an inner function. Inside that inner function, there's another inner function. So the difficulty level increases. Now this is what I'm trying to drive at. The concept that we are teaching here is chain rule. When do we use chain rule? When we differentiate composite functions. Please write it down somewhere. Chain rule is used to differentiate composite functions. That's the concept that we are teaching here. Chain rule is used to differentiate composite functions. That's the concept that I'm driving at this morning. Yep. Chain rule is used to differentiate composite functions. Okay. As you can see, same concept, different types of questions. So my charge to you is know the concept and know where to use it. Because like I said, the questions can change. But once you understand the concept, you can apply it on the questions, no matter how it varies. Again here, what technique do we use? Looks like two functions multiplied together. So we'll use the product rule. F and G. And G looks like a composite function. So that means we will have to use the chain rule here. F dash. So g, I'll write it properly, to the power of half. I'll bring the half down, reduce the power by 1. I get power negative half. The inner function remains the same. And then I'll differentiate this inner function. Get 6x squared. Then I'm going to simplify half and 6x squared. Then I apply the product rule. F times g dash plus g times f dash. Simplify. Multiply this, you can move this to the front. I think there's a group that's doing physics this semester that's going on robotics competition. Anyone involved in it? Probably some of you are involved. And in robotics, differentiation is used a lot and a lot and a lot. Okay. Implicit differentiation is another technique of differentiation. There's some more, and it gets nicer and nicer as we move to the next level. So, one another, says Ben Ryan. In some cases, because, if you can see in the previous examples, we had the equation y equals, or hx equals, or fx equals, or gx equals. We could separate y as the subject of the formula. If that's the case, we can easily differentiate. But there are some cases where you cannot make y the subject. It's too complicated. Special case of differentiation. So in this case, because y is the subject, I can differentiate this set. However, how about this? Where y is not the subject. Now see if you can differentiate. Oh, before you differentiate, can you make y the subject? Quickly. X squared plus y squared equals 4. By the way, does anyone know what this is the equation of? Equation of a circle with a radius of 2. Make y the subject. What do you get? Y equals x squared plus y squared equals 4. Take the x squared to the other side. If I ask you to differentiate this, what technique of differentiation do you use? The chain rule, because there is an inner function and outer function. Shall we differentiate this? Okay. So dy over dx, tell me, what should I have? Let's work on our short methods. Half, okay. Keep going. Inner function remains unchanged. What's the new power? Minus half, is that it? No, I'll still multiply by the derivative of the inner. What's the derivative of the inner? Negative 2x. So the half and the negative 2 will cancel. I don't like the way it looks. Yeah. That's if I use chain rule. But you see, you had to do this again first. There's a shorter way of differentiation. That's why we are introducing implicit, where you don't need to make y the subject. Now, there are some cases where you will not even be able to make y the subject. So rather than racking your brains trying to make y the subject first, we'll move straight on to implicit. Okay, let's have a look. We differentiate both sides of the equation with respect to x. Whenever we differentiate a variable with respect to y, multiply the derivative of y with dy over dx. And then we rearrange to make dy over dx a subject. Okay. Have any more piece of paper? No more. Okay, here. X squared plus y squared equals 4. With those explanations, let's see if we can use technique of implicit differentiation here. We are to differentiate both sides with respect to x, eh? So I'm differentiating the left, and I'm also differentiating the right with respect to x. That's what that means. So let's differentiate. Easy to differentiate the right-hand side. What's the derivative of 4? 0. So the right side is 0. Now I'm going to differentiate, because they are added, I can differentiate them separately. So I'll differentiate plus what's the derivative of x squared? 2x, yay. Plus, now let's differentiate y squared. Because you had x here, you're differentiating x, so you can use the technique of differentiation. Okay? But here you have y. So you cannot apply any technique of differentiation here. The only thing you can do is if I change this to dy. So, over, then I can differentiate y squared. Okay? But the dx cannot just automatically disappear. Because, see, the dx has to be present here, and I also need to cancel the dy, because the dy was not there. So what I will do, I'll multiply this by. That's why you go back to the slide. Whenever you differentiate y, you multiply by dy over dx. Yeah, here. Always multiply by dy over, it's flying away. Always multiply by dy over dx whenever you differentiate y. So that means, where is that? I lost it. Let's go back. So now I can differentiate the y squared. So, what's the derivative of y squared now that I can differentiate it? 2y, and the dy over dx is retained. How much time do we have? Finished? Okay. And then from here onwards, I'll make dy over dx a subject. Take this to the right, take this to the right. Tell me, what do I have? negative 2x over 2y, or which is negative x over y. Now, we did this before. Let's see. Are these two the same? Because they are both dy over dx. Are they the same? Yes, because this is, what is that? Y. So that means this is negative x. I can replace this with y, which is the same as that. Now, it's easier to use implicit. So let's differentiate this. Now, it's going to be difficult to make y the subject. Near impossible. Okay, try making y the subject while we differentiate implicitly. We'll come back tomorrow, you'll still be trying to make y the subject. Fire. So we'll use implicit, we'll differentiate both sides. Differentiate x cubed. Now, this has got a combination of x and y. So in this case, I will use the product rule. So if I differentiate x cubed, what do I get? 3x squared, eh? I'll use the product rule there. X squared. So fg dash plus gf dash. Yep. Now notice there's a minus on the outside here. So differentiate this and leave the minus sign outside. So there. If I use f g dash, oh, here. G is y to the 4, eh? What's the derivative of y to the 4? 4y cubed. Because you're differentiating y's, you'll have to attach dy over dx. And then leave g as it is, times f dash. And then continue the differentiation. The right-hand side, what do we have on the right-hand side? Oh, yeah. Can you differentiate 2y to the 5? What do you get? 10y to the 4 dy over dx, because you're differentiating y's, eh? Okay, let me pick up the pace again. Remember, we're trying to make dy over to find the expression of dy over dx. You've got 2 dy over dx. So we'll have to rearrange. If you remove the minus, everything inside this bracket becomes minus. So we'll change. We'll collect those terms that have dy over dx on one side. The others that don't, we'll collect them on the other side. So I've moved the dy over dx to the right side. It's up to you. You can collect them to the left. And dy over dx is a common factor. I can move it outside of the bracket. And because I'm trying to find dy over dx, take this to the right, to the left, sorry. You'll divide it to the left. So dy over dx equals. See if we have another example. Two functions multiplied together. We'll differentiate them using product rule. Oh, help me out. What's the derivative of 4y? 4 dy over dx. Again, like I said, wherever you differentiate y's, attach dy over dx. 3y to the 4, 12y cubed dy over dx. Differentiate this y, 1 dy over dx. So we'll use the product rule here. One dy over dx times f g times f dash. Minus x to the 4, you'll get 4x cubed plus 4y, 4 dy over dx equals 7, get 0, 12y cubed dy over dx. And then make dy over dx the subject. Those terms that have dy over dx, move them to one side. And those that don't have, move it to the other side. Dy over dx is a common factor on the right side. Then make dy over dx a subject. So yeah. So let's go through what we discussed today. What's the first one? Chain rule. When do we apply chain rule? When we are differentiating composite functions. So with chain rule, there are two functions you need to identify. One is the inner function, and the other is outer. Right? And so what's the technique of chain rule? Differentiate the outer, leave the inner as it is, and then multiply by the derivative of the inner function, and then simplify. And implicit differentiation. When do we apply implicit? When you cannot make y the subject. Yeah? So probably write down somewhere. Use implicit differentiation when you cannot make y the subject, or however you want to phrase it. So set, or write down your name on the attendance sheet. Don't write down your friend's name. Yeah. We'll stop there today. Have a good day, everybody. Again, like I said, I think Ms. Mera has mentioned it. Quiz 1 is opening this Sunday. I do not know what the coverage is, but